This is a neural network trained with a genetic algorithm controlling a snake to eat apples. If you don't know what a genetic algorithm is, you're probably wondering, what's a genetic algorithm? Is it good? How does it work? If you do know what one is, you're probably wondering, is this guy insane? Why would he do that to himself? What's wrong with him? Both of these questions will be answered in this video. If you don't know what a genetic algorithm is, you're not alone. A lot of people never learn these, not because they're hard and advanced like you'd expect, but actually because they're really simple and not that popular, so schools and courses tend to just skip them because it's not worth it. Since we're talking about genetic algorithms on neural networks, you gotta understand how neural networks pass data forward. Basically, you start with a bunch of input numbers. These get passed to a bunch of different neurons who all have their own weights that they multiply each input by, one weight per input, and then each neuron has its own bias, which it adds to the inputs. Then these outputs can all be treated, each individual neuron's output is a number, and that can be treated as a set of inputs for another set of neurons, and you keep going until you get to the end, and then whatever the biggest number on the last set of neurons is, that neuron's chosen as the answer. So if you're trying to guess a shape, like circle, triangle, square from images, you'd have a circle, triangle, and a square neuron, and the largest number on the respective neuron is your guess. You also need, in between each layer of neurons, an activation function, which can be anything as long as it's not linear. Basically just something that says, okay, if it's less than 0, it's now 0. If it's greater than 0, it can keep its current value. And what that does is it prevents the whole network from collapsing into one linear equation. Because think about it, if you take y equals mx plus b, and then you multiply that by some other term, and then you add another term, then you keep multiplying and adding by more and more terms, and then you simplify, you still get y equals mx plus b, it's just a different m and a different b, and neural networks need to be able to learn more than just linear functions, so you add in a slight, simple, nonlinear term. This nonlinear function is called an activation function, and for the sake of this video, I used something called a rectified linear unit, which is a really fancy way of saying if it's greater than 0, it keeps its current value. If it's less than 0, it's now 0. If it's 0, it's 0. Really just truncate the negatives down to zeros. Very simple function. That's all we did, and that makes it so that the neural network can learn insanely complex functions rather than just learning a line. If you didn't understand this, all you actually need to know is that the way a neural network learns is through things called weights and biases, and it changes them slightly or by a lot to be able to learn something. So weights and biases take different values, and that's how a neural network learns. That's all you got to understand the rest of the video. Normally, changing these weights is where people start to get lost. So when people are first starting out, they'll just simplify it and they'll say, all right, we're just going to randomly change the weights and the bias and see if that model does better. If it does better, we'll keep it. If it does worse, we'll lose it and stay with the previous model. And genetic algorithms basically just take that principle to the extreme. The two guys who invented it heard all the calculus, they understood it, they had their PhDs, and yet they were like, nope, I'm not doing that calculus. I just want to keep things random. Let's just do this the fun way. This is Texas. Let's have fun. Their contributions in research gave the world a ton of new science words and pulled a ton of biology words into computer science. So now we have words like neuroevolution, which means using a genetic algorithm on a neural network, but it sounds really cool and like it'd be way more complicated than it is. For a genetic algorithm to work, you usually need 3 things. First, you need a population. In regular evolution, you got a population of animals which wander around. They're all the same species, living in the same place, doing the same environment, and they'll evolve together. In neuroevolution, you usually need a bunch of models that are the same shape, have the same number of weights, same number of biases, and the same activation functions. So basically, they're all the same in structure, but they have a bunch of different weights and different biases and all that stuff. We also need a way to kind of eliminate models that don't get to survive, kind of a natural selection. In nature, an animal either eats something and survives, or it becomes someone else's food and it dies, and it doesn't get to pass its genes on to the next generation. In neuroevolution, we do roughly the same thing, except instead of having an actual system, we're literally just arbitrarily handpicking models on any criteria we want. That is way simpler than most forms of deep learning because you can literally just take the best models. It makes it super easy for real applications like, hey, the snake versus just learning to a labeled data set. It's way easier to carry over. So, for example, you could look at the 5 highest scores on the game snake. You could make your own arbitrary score. You could train something for golf and take the 5 lowest scores. Or you could take the score that's closest to the number 7 on some arbitrary game or anything. It's super easy and super arbitrary. You just gotta find a way to handpick models and handpick models that favor that thing and let those models survive to the next generation and then kill off the majority of them that are less so in that trait. So 5 highest scores and then kill off the next 100 or something models. Once we've taken the best models from our population, we can use them to create a new population, the next generation, in a few different ways. First, we can just take an exact clone of our best models because they're good models. Second, we can also randomize them very slightly to make very slightly different models, like a random optimizer someone might use if they're brand new to training AI. The third thing we can do is actually really weird. What we can do is we can make a hybrid model. Imagine model A's weights as a list and model B's weights as a list. If we at random pick weights from model A and model B to fill a new list of the same length. So the 0th weight we can pick from model A or model B's 0th weight, and then the first weight we'll take from model A's or model B's first weight at random all the way down the line until we have an entirely new model made out of model A and model B's weights, but completely different. We can also optionally randomize this. I didn't in this project, but you can. I didn't think this was gonna work or be useful or do anything other than completely kill off every model it produced going into this, because think about it. Normally a neural network works because a bunch of different neurons all do their own jobs and they kind of combine to make one greater picture. For example, take 2 4-neuron networks. Maybe the first one has neuron 1 do job A, neuron 2 do job B, neuron 3 do job C, neuron 4 do job B. And the second one might have job D done by neuron 1, job C done by neuron 2, job B done by neuron 3, and job A done by neuron 4. Now, if you swap out the weights from these 2 different neurons, you're going to end up with a bunch of neurons that don't do any jobs and just predict the wrong outputs. Rather than trying to guess what was going to happen, I decided to just dive in and train the model and see what happened. I used PyPearl version 0.4.9. It's my own machine learning library that I added genetic algorithm support for. You can try it if you want. Just know if the version starts with a 0, it's not stable. Next, I needed the snake game, so I just followed this guy's tutorial for Pygame snake because I didn't know how to use Pygame. But I did know that Pygame, unlike game engines, lets you just boost the FPS over and over again and let the game basically run really fast and even shut off the screen and shut off everything that makes the game visual and just have the calculations run, making it go insanely fast, letting me train the model for over a year of in-game time in just one day. Then whenever I want to see my progress, I'd just stop the training, turn back on the screen, lower the frame rate, and I'd get to see one of the models moving around and how it moved and what it was doing. First, I needed to decide the structure of my neural network that would attack this problem. That means I need an input vector of constant size that I know what it's going to do, an output vector of constant size that I know what it's going to do, and then some inner size that's going to be the same every time that I'm not going to know what it's doing. I also needed to simplify the problem so that my input and output would get to be as simple as possible, and the inner size could be smaller and still understand the whole problem. So I decided to remove the part of traditional snake games where the snake gets longer and longer and longer, where the challenge comes from, because here the challenge comes from it being an AI model trying to figure out what's going on instead of it being a person playing. But if you guys like and subscribe, then I will go back and maybe I'll try to do it with a longer snake. We'll see what happens. Since I removed this challenge from the game and a core part of the game is the snake hitting itself, I thought, Well, an AI doesn't really know what direction it's going to move in, at least at first. So what if I kept it so that if it backs into itself, then it just loses instantly? Normally in a snake game, if you press the arrow that's the opposite of the direction you're moving, it just doesn't do anything, it just ignores the input. So I made it so that if you press the arrow opposite direction you're moving in, instantly you lose. For this problem, inputs are a vector rather than a matrix. In a normal dataset style neural network problem, you can do all the inputs at once and treat them as a matrix where row 1 might have two things, person 1's height and person 1's weight, and it's got to guess the BMI of person 1. Then row 2 is person 2's weight, person 2's height, and it's going to guess the BMI of person 2, and so on. And the BMIs are all labeled, and that's a while, and you could just do a matrix through the whole network as once because they don't depend on each other and they all have labels. But for this, the next input depends on the previous output. You get where you are on the board, you move somewhere, and then you input in where you ended up and how the board looks relative to the new position. So if you were to input the next 10 positions, you wouldn't know what they are because you need the outputs. So instead, you just pass one row of inputs at a time and just do a series of inputs over time. For the input vector, I needed to encode everything the snake needs for information to be able to win the game. That means the snake from the input vector needs to be able to figure out how to not back into itself, not walk into a wall, and how to find an apple. That first thing, not backing into itself, the only way to do that is to go in the opposite direction of the direction it's currently moving in. That means I just need to have a way to encode which direction it's moving in. I decided to take the first 4 neurons. If it's +1, that neuron represents the direction you're moving in, and then the other 3 neurons will be 0, and then 1 neuron's for up, 1 neuron's for the right, 1's for left, and 1's for down. Used a very similar method for each of the 4 walls, but with the 4 walls, you also need a distance. So what I did was I took 20, that's the length of the board, and I took the distance of the snake head to the wall, and I divided the distance by 20. That means as you get closer to 0, you're closer to the wall, and you need to be very careful going even closer to the wall, and that was enough information for the snake to learn to avoid the walls. Finally, the snake just needs to know how to find the apple. To do this, I took the X and Y coordinates of the apple, and then subtracted the X and Y coordinates of the snake, and then I used those as the inputs, but I scaled them by the sum of their absolute values +1 so that there'd never be a divide by 0. It's not exactly a unit vector, but it's good enough that it'll be between 0 and 1 and show roughly how to get to the apple, and it's good enough for the snake to learn. The way you pick a shape of a model is you want to pick the smallest model that can still learn the pattern. If your model's too big, what ends up happening is 1, it gets really slow because of more multiplication and addition operations, and also it just takes more generations for a model to learn a more complex pattern because there's more weights that need to be able to change for the function to work. But also what can happen is the model can learn too complex of a pattern where it, say, looks at one square with one apple placement and it sets a certain pathway from input to output for that specific placement, and then another placement, and then another, rather than creating a general trend of, if I'm not about to hit a wall and the apple's above me, I'm gonna go up. If I'm about to hit a wall, I'm gonna turn away from that wall. If I'm a general trend versus an actual memorization of a bunch of different discrete spaces. The other thing you got to worry about is a model that's too small can't learn anything. If it's, say, 1 neuron, it's not going to learn that much. It's going to learn, okay, if I get too close to the right wall, I got to go away from the right wall. But it won't be able to also learn the top wall, the left wall, the bottom wall, and to go towards the apple. It's just not enough weights and biases to encode all the information the problem needs. I ended up choosing a model that had 10 inputs and 4 outputs, but also 32 neurons on each hidden layer and 2 hidden layers. Honestly, this was probably a bit bigger than I needed, but it ended up working, so it's fine. Finally, I needed an output layer. Basically, this is how we translate the model's calculations back into a change of state in the space. So normally, you can really make these anything. Like, for example, I could have 1 output neuron that's just go closer to the apple, and only one output neuron. The model's always going to pick that, and it's really overcomplicated, but it's basically just running an algorithm, so that's not a good way to do this. More simply, what I could have done is I could have said you can continue in your current direction, you can turn left, or you can turn right, which, remember, one of the challenges of this problem is the model's going to learn to not back into itself, and that removes that challenge. So that's not a great option either. So instead, I just decided 4 output neurons, WASD, or your arrow keys. It'll get treated exactly the same as a player clicking those arrow keys, and therefore there's no like playing around with the model's outputs to make anything fast. It's just you pick the direction you turn, and it turns that way, and the model can very easily back into itself and terminate itself early. The first issue I had was that the snake was learning to only go to the left because it would always spawn moving to the left, and then if it chose to go to the right, its first few actions, it would instantly be killed off. So only the snakes that would only move to the left or left and up and down made it to the next generation. And after like 300 generations, I had snakes that would ignore the apples and just go up and down and up and down, and it just wasn't good. And they'd eventually hit the right wall, and they would never go back to the right, never even think about the apple. I fixed this by randomizing the spawn point and the spawn direction, so the snake can spawn all over the place doing a bunch of different directions. But also it occurred to me, this snake can just run laps around the board and ignore the apple, and as long as it doesn't die, it scores theoretically infinite. So I decided it gets 8 seconds between each apple, or else it's gonna die. And that made it so that the model was actually focusing on getting the apple. Now that I have the whole problem laid out, I just need a way to breed the models for things to actually learn generation to generation. First, I would take the top 5 models of every generation and pass them directly on to the next generation. I don't want to lose a really good model in some random just deciding to breed them all or randomize them all. So top 5 models always got to stick around. Then they'd also get a clone of themselves that was randomized on its weights, kind of like a genetic mutation if we're going by genetic algorithm terms, to pass on to the next generation as well. Finally, I would give 10 models that were made by breeding. The first model would breed with the other 4 models and it as the primary parent, and it would create 5 more models. The second model would breed with the other 4 models, and it would create 4 more models. Then the third one would breed as the primary parent with the first and second model, creating a total of 10 more models. So each generation would have exactly 20 models. After this, I kind of just let train and rip, and whenever I'd hit a plateau, I'd go in and I'd change one of the factors. For example, the randomness mutation thing, I might add a 0 in front of that parameter so that the models get altered in the randomness phase a bit less because now they're better, so they only need slight improvements versus just trying to find something that might be good. And the breeding factor, I'd also make it so that models would be more of one parent than the other. And that way, if a parent's really good, but it could use a bit of help, maybe something to shake it up, maybe it's got 32 neurons and 24 of them are doing all the work, a lower breeding factor could keep 24 of them or 22 of them doing a good job and maybe make 6 of them do something that might help if you do it enough times. After 25,000 generations, or about 7 months of the AI playing, I had a really good model. It just had one small issue. Every now and then this model would run and then it'd hit a spot where it would just walk in a circle over and over again until it died out. And I realized the issue here was that instead of after eating each fruit, the snake had 8 seconds to live, it had 8 more seconds to live. Notice the difference there? Every time the snake resets, it's adding 8 seconds to its total life. So if it eats a fruit, eats another fruit, eats another fruit, all of a sudden has 24 seconds. And this can stack up to be a really long time. So the snakes had a few wells where they would just stop and run laps over and over again. And this turned out to be somehow better, like a local maximum, versus trying to actually learn to perfectly hit every fruit. Because when it's doing a lap, it's not going to die. So it's just going to collect all the points from all the fruit it ate. And these models, for whatever reason, were prevalent. This was actually a really easy fix. I just changed it from adding 8 seconds to resetting its 8-second counter. So instead of eating a apple with 5 seconds left, leaving you with 13 seconds on the clock, it now puts you back to 8 seconds. And after this, I ran the model for another 1,000, 10,000 generations or so. And after that, it's the basically perfect model you see in the video that really just never dies. The only way I was able to not make it an infinite loop is I actually set the time to less than 8 seconds, which was less than the time needed to get across the map. So the models were basically all going perfectly until a fruit spawned too far away that no matter how perfectly it would move, it still wouldn't make it to the fruit in time. So this proved that genetic algorithms can train neural networks, but keep in mind, we already knew going into this that a random optimizer, if you just throw in a random number, like the genetic mutation phase, would eventually get you something, and we did go through 40,000 generations. So was the breeding factor actually doing anything? Well, early on, we know that everything's just chaos. If you take 5 randomly generated models and then you breed them together to get a bunch of new randomly generated models, the bred ones are probably just as likely to hit anything as the randomly generated ones. That wasn't really our concern. Our concern was when you took 2 models that were kind of working and you merged them together to make a model that would hopefully work a bit better. So what I did was I decided, let's look at every single output of the current generation, the 38,000th generation, and train it for 5 more generations and just look at each individual generation. Do the bred models pass on, or do the not bred models pass on? Is it only the perfect models? I was actually really surprised by these results. As you can see, yes, a lot of the time it's the bred models can be the worst of the models, but a lot of the time they're as good or better than the models that are already really good at their task. And it hit me, it's because these networks are all evolving together in parallel. They all end up with a similar structure. Each neuron does a similar job. So maybe if a neuron does better, if a network does better, it's because it found a way to improve one neuron better than the other networks. But if another network found a way to improve another neuron a bit better, and each of those are just one weight change, then you could combine the 2 weights, and if you get lucky, you'll get a model that's a lot better than all the other models, because the 2 best models had one advantage and they just shared their advantages. Will that always happen? No. Some of the worst models from this repetition were also from breeding, but it helps, it works. Thanks for watching, and subscribe if you learned something about genetic algorithms.